So the idea of a basis is actually pretty important. They are essentially the building block of the vector space. I'm gonna say that vectors v1 to vn are a basis of a vector space V if these vectors are linearly independent. So I want them to be linearly independent. I don't want any of them to be dependent of the other, and I want them to span the vector space. So let's actually think of the basis in the usual real space. So let's say I have the R squared, the usual plane. The basis for this space that we usually think of are the vectors 0, 1. Wait, this is 1, 0. The vector 1, 0 and 0, 1. Notice how these two guys, they are linearly independent and they span the entire R squared. Now, for the R cubed, the usual basis that we will think of are the vectors 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. Wait, did I say too many? I think I said too many 0, I mean 0, 0, 1. So now notice again that these three guys, they are linearly independent and they span also the entire vector space. And that's the same for, well, any higher dimensional. If I have R to the 4th, the usual basis that you will have, like 1, 0, 0, 0, and so on. These guys, they are linearly independent and they span the vector space. So now, what this definition actually does is that it actually kind of allows us to think of a basis in a more broad sense. So for example, the basis of a vector space are not going to be unique. Let me actually kind of write that down. Bases are not unique. Right. For example, in the R2, I can now say that this vector 2, 1, and let's say another one, this vector 1, 2. This is also a basis for R squared, and that's because these two guys, they are linearly independent and they actually also span V, or I can just make up another one. So as long as the two vectors are linearly independent and span the entire R squared, these two guys are always going to be my basis of R squared. So they can be anything. So there's actually a bunch of possible choice of basis here. Bases are not unique. Now, there's actually two important properties of a basis. If V1 and V1, V2 to Vn is a basis for a vector space V, then every vector U in V can be written uniquely as a linear combination of the basis. And this makes sense if you think about it. If I have any vector in R squared, this vector can be written uniquely as something times this guy plus something times this guy. And also, the dimension of a vector space is the number of bases for the vector space. Now, you might notice, if I have a vector space, no matter how I write the basis for that vector space, the number of elements in the basis are going to be the same. No matter how I write the basis for R squared, the number of bases are going to be just 2. No matter how I write the basis for R cubed, the number of bases in this guy is going to be 3. So the number of elements in the basis are going to be unique for that vector space, and that number is called the dimension of that vector space.